This video is sponsored by Squarespace.
Today I want to look at something known as the quantum derivative, and we'll do some basic examples and look at how it relates to the normal derivative. Okay, so what is this quantum derivative? Well, here it is. I'll say that the quantum derivative operator is denoted by d sub q, and if you apply that to a function f of x, you get f evaluated at x times q minus f of x over x times q minus x. And you might say, well, what is q here? Well, q is a formal variable. So you can think about like extending the real numbers to this world where you have formal power series in this variable q. But now here's where I'll contradict this, because sometimes we take the limit as q goes to 1. That's an interesting thing to look at. And you might say, well, where is this useful? Well, it's useful in the combinatorics of a certain structure known as a quantum group. So maybe post in the comments if you'd like to see a video about quantum groups, although they are quite technical. Okay, so I think probably the first thing we should do is calculate some very basic examples. And so that's where we'll start. So probably the first off, we could take the quantum derivative of just the function x, the identity function. But notice by this rule over here, that'll simply give us xq minus x over xq minus x, which is simply equal to 1. But the normal derivative of x is also equal to 1, so they at least line up when we're taking the derivative of x. Now let's take the derivative of x squared. I should say the quantum derivative of x squared. So that'll give us, let's see, x times q squared minus x squared over xq minus x. But now we can factor that numerator like a difference of squares, and that'll give us xq minus x times xq plus x. And then we still have this denominator, xq minus x. But now notice we get some nice simplification here. And then what we're left with, we can factor an x out, and that's exactly what we'll do. And then I'll rewrite this as 1 plus q times x. And then important to notice is what happens if we take the limit as q goes to 1, we get 1 plus 1 times x, in other words, 2 times x. So with the limit as q goes to 1, we retrieve the normal derivative here. Okay, well, let's maybe do one more basic example before we prove the quantum power rule. Okay, so let's maybe do dq of x cubed. So let's see, that'll give us xq cubed minus x cubed over xq minus x. But now in the numerator, we can use this difference of cubes formula, which is pretty similar to the difference of squares formula. So that'll give us xq minus x times xq, both of those squared, and then plus x squared times q, and then finally plus x squared. And then all of that is over xq minus x. So that factorization via a difference of cubes may seem a little bit weird in this case because there's lots of x's and q's floating around here. But let's just recall that we have a cubed minus b cubed factors as a minus b times a squared plus ab plus b squared. It just turns out in this case, what do we have? Well, we have a is equal to x times q and b is equal to x. So that means everything in this object right here with the quadratic terms will have a term that has an x squared in it. Okay, so anyway, notice that we get some nice simplification here, just like we did before. And then we can factor an x squared out of this. Maybe we'll factor it out of the right-hand side, and we'll be left with 1 plus q squared. But notice as q goes to 1 in this case, we get exactly what we want again. We get 3 times x squared. Furthermore, the structure of this like q polynomial that's popping up in front of everything is starting to take shape. Here we've got 1. Here we have 1 plus q. Here we have 1 plus q squared. Well, look, those are just sums from 1 to a power of q, which is 1 less than what we started with right here. So I think that gives us a hint as towards the power rule. Now let's state and prove that.
Before we continue, I'd like to thank today's sponsor, Squarespace. Squarespace is a service that takes the hassle out of creating a website. You don't have to be a programmer or a graphic designer to have a professional looking website. Because of their support, I can dedicate all my spare time to doing the things I love. With Squarespace, you too can focus on what's important to you and leave the technical stuff to them. With the new Fluid engine, you have complete control over the structure of your website. The simple drag and drop action will help you get your site online quickly, and access to analytics will help you tailor your content to your audience. I use Squarespace for my website, and I find it easy to use with plenty of integrations. They even have a plugin for LaTeX that allows me to write equations very easily. Whether you need a place to sell your merch or show your art, Squarespace has the tools you need to keep your website modern and easy to use. So what are you waiting for? Give Squarespace a try by going to squarespace.com/michaelpenn to save 10% off your first purchase of a website or a domain using code michaelpenn. Thanks once again to Squarespace for sponsoring today's video that we are now returning to.
So based off what we saw on the last board, I think we can reasonably guess what the power rule should be, and that's exactly what we'll do, and then we'll prove that guess is true. So for all natural numbers n, the quantum derivative of x to the n is 1 plus q squared up to q to the n minus 1 times x to the n minus 1. So still we have this process of decreasing the power by 1, but instead of multiplying by the previous power, the previous exponent, we've got this like q polynomial term. That being said, notice if q were to approach 1, we would have 1 plus 1 plus 1, well, a bunch of 1s. How many exactly? Exactly n 1s. So let's make that observation right over here, that if we were to let q approach 1 here, we would get n times x to the n minus 1, the normal power rule. So I think that's probably setting up a guess in our minds as to the relation between this quantum derivative and the normal derivative. But we're not quite there yet. Let's prove this quantum power rule. Okay, so let's take dq x to the n. Notice that'll be x times q to the n minus x to the n over x times q minus x. Now from here, what I'd like to do is factor out as many x's as I can from the numerator as well as the denominator. So let's see, from the numerator, I can take an x to the n out, and from the denominator, I can take an x out, and I'll put them over there on the right-hand side. Then in the numerator, I'll be left with q to the n minus 1. In the denominator, I'll be left with q minus 1. Oh, but there's like a nice difference of n powers formula that we can use to simplify the numerator. This in fact factors as q minus 1 times q to the n minus 1 plus q to the n minus 2 added all the way down to q plus 1. But that means that q minus 1 cancels from the numerator to the denominator, and we're left with exactly what we need. So 1 plus q all the way up to q to the n minus 1 times x to the n minus 1. Of course, after simplifying that x to the n over x. Okay, and then that actually motivates the following definition, which is really like what we would maybe call a q analog of the natural number n. Now, if you watched my video on the quantum binomial coefficient or the quantum factorial, you've seen this before. And that is, we'll set n bracket q, so that's the q analog of the number n, equal to exactly this object right here. So we have 1 plus q squared ending at q to the n minus 1. But sometimes we write this as the quotient 1 minus q to the n over 1 minus q, which simplifies to what we had before. Then we can employ this definition in this power rule to rewrite it as the q analog of n times x to the n minus 1. And now if we compare what we have on the extreme left and right hand side, we really have something that looks like the normal power rule. And furthermore, if we take the limit as q goes to 1, we do get the normal power rule. Now, what we'd like to do from here is prove that relation between the quantum derivative and the normal derivative that we have been alluding to. Now we're ready to do it. We're going to show that the normal derivative f prime is the limit as q goes to 1 of the quantum derivative. So that gives us this nice kind of multiplicative version of the normal difference quotient. I say multiplicative version because we're moving the inputs into the function together via multiplication instead of addition. Okay, great. So let's maybe get to it. So let's start with the right-hand side. We have the limit as q goes to 1 of the quantum derivative of f of x, but I'll just rewrite it as this quotient. So we have f of qx, or xq, minus f of x equals xq minus x. And now from here, I'm going to make a change of variables. And really, that's all you have to do. Make a simple change of variables, and then we'll be home free. And that change of variables will be to set q equal to x plus h over x. Okay, but now let's notice what that does for us. First of all, that tells us that x times q is equal to x plus h. And then solving for h, we see that h is equal to x times q minus x. So as q goes to 1, we see that h goes to 0. So that tells us how we need to change like the limiting portion of our limit. Okay, so let's maybe see what we get out of this. This is going to turn into the limit as h goes to 0 of f of, well, notice that xq is x plus h. So there we have that. And then minus f of x, that doesn't change, over xq minus x, but that's exactly h. Oh, but look at what we've retrieved. We have retrieved the standard definition of the derivative. So this is in fact equal to f prime of x, maybe as needed. Okay, so next up, let's look at a quantum product rule. Now we're going to look at a quantum product rule. So let's just get at it. We're going to take the quantum derivative of the product of two functions f of x and g of x. Okay, so just applying this rule over here, we'll have f of xq times g of xq minus f of x times g of x over xq minus x as needed. And now we're going to do a mathematician's favorite trick, or at least one of our favorite tricks, which is adding the number 0. And we'll add the number 0 to the numerator. And we really have two choices here. And that's because there are two expressions, well, they're equivalent expressions, but there are two expressions that we could write down for this product rule. So we'll only do one of them, but you can check the other one as well. So what we will use is subtracting f of xq times g of x and then adding it back in. So plus f of xq times g of x. So of course, that's just like adding 0. So the other choice would be to subtract f of x times g of xq and then add that back in. So f of x times g of xq. So like I said, we're going to go on with this first choice, and we're going to do that into the numerator. So that'll leave me with f of xq times g of xq minus f of xq times g of x. That's from subtracting this term. And then I'm going to go ahead and put these all over this denominator because I'm going to split this into two pieces. And then I've got this term, the thing that we've added in. So plus f of xq times g of x, and then from that we need to subtract f of x times g of x, and that's all over xq minus x. But look, we've got some common factors in the first term and in the second term. Here's our common factor in the first term, this f of x times q, and the common factor in the second term is simply g of x. Okay, nice. So let's factor those out and see what we get. So factoring out of the first term, we'll have f of xq, and then to that we will multiply g of xq minus g of x over xq minus x. And then factoring out of the second term, we'll have g of x. Actually, I'm going to factor it out of the right-hand side just because I like keeping things in order. And we'll be left with f of xq minus f of x over xq minus x. Oh, but check it out. This first bracket is the quantum derivative of g, and that second bracket is the quantum derivative of f. So that gives us f of xq times the quantum derivative of g, and then plus the quantum derivative of f times g of x. So notice it doesn't exactly look like the product rule, and that's because, well, this is an f of xq instead of an f of x, but it is very close to being a product rule. Okay, so there's also a quotient rule that has a pretty similar structure to what the normal quotient rule has. There's just like an extra xq in there somewhere. Okay, so now I'd like to look at some typical quantum functions and really how to build those quantum functions. Now we're going to look at how to find quantum versions of your favorite functions. So here's the basic idea. So you take your favorite function f of x and you expand it as a power series. So I guess that kind of restricts you to functions that can be expanded as power series, but you know, we have to restrict ourselves somehow. So this is going to be equal to the sum as n goes from 0 to infinity of a sub n times x to the n. So there I've expanded it. And I guess you could center it somewhere else if you wanted to, but we'll just center it at 0. And then here's the hope. So the hope is that this number, a sub n, is a rational number. So let's put that here. So hopefully this is rational. Well, that's because we're going to take all of the natural numbers, which if it's rational, it's a natural number over a natural number. We could take the sign outside and we're going to replace all of those natural numbers with their quantum versions. So that's what we'll do. So then we'll take what I'll call the natural number components of a sub n and replace with the q analogs. So let's see what that gives us. So that'll give us something that I'll maybe just write like this. So f sub qx will be the sum and goes from 0 to infinity of, I'll just write this as a sub n q, where that's the replacement that's been done, and then x to the n. Okay. So now let's do this with some nice functions, if you will. So maybe a polynomial first. So let's take 1 plus 2x plus maybe 3x squared. So what would the quantum analog of this be? Well, it would be 1 plus, well, you know, the bracket 2q, but remember bracket 2q was just 1 plus q times x. And then we'll have bracket 3q. So that'll be 1 plus q squared times x squared. So there's a quantum version of that polynomial. Now, what about the exponential function? So we know e to the x can be written as the sum as n goes from 0 to infinity of x to the n over n factorial. Well, in order to find the quantum version of that, well, we'll exchange the n factorial for the q analog of n factorial. So I'll write this as e sub q of x will be the sum as n goes from 0 to infinity of x to the n over the q analog of n factorial. And let's just recall what that is for a second. So the q analog of n factorial is equal to, well, let's see, it'll be n, well, the q analog of n times the q analog of n minus 1 all the way down to the q analog of 2. Of course, you would also need the q analog of 1, but that's simply equal to 1. And then, well, you would make all of the necessary replacements here. So let's see, we could replace all of these. This will be 1 minus q to the n over 1 minus q. This will be 1 minus q to the n minus 1 over 1 minus q. All the way down, this will be 1 minus q squared over 1 minus q. So we can actually mash all of that together and we'll end up with the following product. So it'll be this descending product, 1 minus q to the n times 1 minus q to the n minus 1, all the way down to 1 minus q. You might say, well, here we stopped at 1 minus q squared, but I'm actually gonna include another 1 minus q over 1 minus q just to like fill this out. And then we've got a product of a bunch of 1 minus q's. How many? Well, there are exactly n. So we might write this as 1 minus q all to the n power. Then we can rewrite our exponential or our quantum exponential function using that. So here we have the sum as n goes from 0 to infinity of, let's see, we'll have 1 minus q all to the n power over, I'm going to introduce this symbol, it's called the Pockhammer symbol, q sub n, and that's just exactly this numerator here. Notice it flipped upside down, and then times x to the n. So there we have it. That is our quantum exponential function. So let's maybe read it from here to here. And it satisfies exactly the rule that you would want it to. If you take the quantum derivative of this, you just end up right back with that. And using this strategy, you can find a quantum sine function, a quantum cosine function, and so on and so forth. And actually, like, an interesting game to play is to plot maybe these quantum exponential functions with different values of q. Of course, you can't plot it unless you set q equal to a number, or at least you can't plot it on a plane unless you set q equal to a number. So if you start at like a small value of q, a q value close to 0, and work up to a q value close to 1, you will see the graphs of these limit to the graphs of the normal exponential function, which I think is a nice exercise. Okay, so if you've stuck around this long, well, thanks. And if you haven't subscribed yet, maybe consider subscribing. It really helps the channel out, and that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.